So in this lecture, let us discuss what is Jacobian matrix. Alright. So let me take u equal to f of x comma y and v equal to uh, g of x comma y. Alright. Now for this, so first you write what is derivative of u with respect to x, right? And then derivative of u with respect to y, because u is a function of two variables. That is what. And derivative of v with respect to x and derivative of v with respect to. So this is the Jacobian matrix for u and v. Okay. Maybe before discussing the Jacobian matrix, we must talk about a transformation. I hope we already discussed what are linear transformations, right? So linear transformation. Okay. So for a linear transformation, if you see its matrix representation, that is nothing but a Jacobian matrix. See, for example, if I have a linear transformation from R2 to R2, all right, and which is defined like this, which is defined by P of x comma y is mapped to 2x plus 3y, and this is 4x plus 5y. Let's assume this is how the linear transformation is defined. Now, if I compare with it, what is u here? U equal to 2x plus 3y, and v is nothing but 4x plus 5y. Okay, so let me compute what is a Jacobian matrix for uv, and so let me write the Jacobian matrix for u comma v, okay, with respect to x and y. Now here let us write Jacobian matrix for this u and v. Okay, so all that I need to do is derivative of u with respect to x here, and derivative of u with respect to y, and derivative of v with respect to x, and derivative of v with respect to y. So what will it be? So you see that this is derivative of u with respect to x is 2, and with respect to y is 3, and with respect to x, derivative of v is 4, and this is 5. All right. Now, if you observe that, if you write matrix representation of a linear transformation with respect to standard basis, you see what is the image of 1 comma 0, which is actually 2 comma 4, and our first column is 2 4. If you observe, all right. And similarly, I hope we can see the second column. I mean, to see that, we need to know what is the image of 0 comma 1, which is actually 3 comma 5. Okay, so whenever the transformation is linear, then the Jacobian matrix is nothing but matrix of the linear transformation. Okay, but in non-linear case, how we can see that? How we can see this Jacobian matrix? And there is one more specialty about this Jacobian matrix, because whenever you have a linear transformation, let's say let me do one thing. Let me take some rectangle here, not the rectangle, maybe I'm taking the linear transformation x of y. I'm defining some new linear transformation. Let me name it as t naught, which is 2x comma 3y. Okay, so here if you observe that along x-axis, whatever you take it on x-axis, its length is going to be extended by 2 times, and on y-axis, its length is going to be extended by 3 times. That's what is going to happen. It means if I take a unit square in xy plane, okay, so this is what xy plane. Now let me assume the other guy is uv plane. This is uv. Okay, so uv plane, I'm drawing it here. So now if you see the boundaries, now the boundary lines are nothing but this is actually x is not x, this is y equal to 1, and this is, sorry, x equal to 1, and this is y equal to 1. Right, this one is x. And similarly, this is y equal to 0 and x equal to 0. You can see it here. And if you see image of these line segments under this mapping, this x equal to 1 will be mapped to x equal to 2. What I mean, you see what is the image of 1 comma 0. 1 comma 0 image is nothing but 2 comma 0. It means this line 1 0 is mapped to 2 0. And similarly, if you see the point, this corner point, that is 1 comma 1. So the image of 1 comma 1 is nothing but 2 comma 3. I'm using this linear transformation. Okay. So 2 comma 3 is somewhere here. And similarly, if you observe the other boundaries, so this is what the guy you're going to get. So the red color lines are nothing but images of these unit Q. Okay. Now the major observation here is the area is expanded. All right. So earlier, if I see the area here, so the area, so area in XY plane. Okay. So I'm actually taking some region R. So the area of R in XY plane, and this will be equal to, is it equal to area of P of R? Maybe let me write it like this: area of R. So initially the area of unit cube is 1. Okay, after transformation the unit cube became this, and you can treat it, this is R, and whereas this is T of R. Now what is the area of T of R? You know, this point is 2 comma 3, no? So it means its length is 3 and width is 2, therefore its area is 2 into 3, which is 6. So whenever you apply some transformation like this, the area is either going to be expanded or maybe compressed or may remain same. It depends on the transformation. For this particular transformation, this expansion is happening. Now the question is how to know this change in area. So now this change in area, which can be found by taking determinant of Jacobian matrix. Okay, you see the Jacobian matrix. So for this one, what is the Jacobian matrix? Let me calculate. If I consider this is U1 V, okay, the Jacobian matrix here is nothing but 2, 0, 0, 3. This is the Jacobian matrix. All right. J of U comma. Now, what is the determinant of Jacobian matrix? Is nothing but 2 into 3, which is 6. Okay. Now, actually, the relation what we have here is this. So, if you take area of R, okay, and area of P of R. So the relation, you can tell me what is the relation here. So this is actually the Jacobian, determinant of the Jacobian matrix into area of R will be equal to this. Okay. So this is the relation you can write. Where this J I mean Jacobian of U comma V with respect to X comma Y. Okay. Whereas if you want to write it in the other way, okay, if you want to write it in the other way, where I'm treating this is XY plane, this is an XY plane, and this is in UV plane. The other way you can write it like this: area of R in XY plane, that equal to Jacobian of X comma Y with respect to u comma v. Yeah, you may ask me what is this notation means. This is the determinant of the Jacobian matrix. So this is actually that of Jacobian matrix. If it is that of Jacobian matrix, I'll simply write J or mod J like this. Okay, so this Jacobian into area of T of R. That's what in UV plane. Okay, so this is not only true for linear transmission, it is true for any non-linear transmission also. So it is applicable for non-linear transmissions also. Okay, I'll give you some example. You can see some application of Jacobian simply like this. For example, you are asked to find area of an ellipse. That is given by x square by a square plus y square by b square equal to 1. Alright, so find, the question is to find area of an ellipse, right? So how many of you know what is the area of an ellipse? This kind of ellipse. What is the formula? Without searching, you tell me. Don't Google it. If you know, frankly tell me. Otherwise, okay, don't reply.
సార్ మీరు రాసింది అనుకుంటారు ఏరియా ఫెసిలిటీ.
What is it? What I mean, area bounded by an ellipse. Area bounded by an ellipse.
సార్ మీరు రాసిన ఫార్ములా సార్ ఏరియా ఫెసిలిటీ.
Come again, I didn't understand. So the question is to find area bounded by an ellipse. X square by a square plus y square by b square equal to 1. It is just an equation. Suppose if the question is what is the area bounded by the circle x square plus y square equal to 1, what is the answer? This I hope you can tell me. Area of a circle, what is the formula? Pi r square. Do you remember? Area bounded by a circle with radius r is nothing but pi r square. Right? So since it is unit circle, its radius is 1. So its area is 1. Sorry, its area is pi. So if the question is about circle, it is easy to answer. Alright. So now what I'll do is to answer this question, I'll take help of Jacobian transformation. I mean, a transformation and the Jacobian determinant. With that, I'll try to find area of this ellipse. So you try to see what I'm going to do now. So initially we have a picture like this. The picture is there in the UV plane. Sorry, XY. So this is X and Y, and now I need to draw an ellipse, right? So I'm very bad at drawing. It is even though it doesn't look like an ellipse, you accept it as an ellipse. Okay. So let me assume this is A, and this is the point B. I mean 0, B here, A, 0 here, and this is the equation for x square by a square plus y square by b square equal to 1. Okay. So now I'll do one thing. I'll try to choose a transformation so that this ellipse becomes a circle. Okay. So you try to apply a transformation so that this circle becomes an ellipse like this. Okay. It is looking like big boss symbol, right? A circle in the ellipse. Anyway. Now to do that, so what I'll do, I'll apply, I'll take this transformation, I'll choose the new coordinates. The new coordinates are u equal to See, first let me observe this equation. This equation can be rewritten like this. This one can be rewritten as x by a whole square plus 5 by b whole square equal to 1. Okay. Now if I assume this entire expression itself is some variable, then it looks like u square and v square equal to 1. U square plus v square equal to 1. What I mean, you choose the new coordinates, that is u equal to x by a and v equal to y by b. Alright. So what is the Jacobian? Sorry. What happens to this equation now? Let me assume this is 1. Now 1 transforms this way, right? Now 1 implies u square plus v square equal to 1. You see? So just by applying this transformation, now this ellipse becomes a circle. Means if you draw the plot of it, so let me draw it here. Now after transformation, after applying transformation, let's say this is the picture we have. Okay, this is a circle. It's not exactly looking like, but assume this is a circle, right? And whose equation? I mean, let me tell you what are these axes here. So this is actually v axis and this is u axis. Means here picture in the xy plane you had it, and after applying transformation, the picture in the uv plane is this. Okay, now you're completely changing your coordinates. It's a kind of changing basis in the vector space and looking at the objects. It's a kind of that. All right. Now you know what is the area of this circle. What is the area here? Area bounded by u square plus v square equal to 1, that is given by pi r square, that is pi into 1 square, that equal to pi. But what is our interest? Our interest is to find area bounded by the ellipse. So now let me mention here, now our region in the xy plane, that is nothing but region bounded by ellipse. Okay. Whereas after applying mapping, let me assume this is the mapping we applied. Need not be linear transformation. We applied a transformation. After applying transformation, this T of R, this becomes region bounded by circle. Okay. Now earlier we have seen what is the relation between the area of R. I'm using this A of R for area. Okay, area of R and area bounded by T of R. We already see the relation. The relation is nothing but here we need to take the Jacobian. And what is a Jacobian here? This Jacobian is nothing but, since it is in xy coordinates and it is in uv coordinates. All right. So here I have to take Jacobian of x comma y with respect to u comma v. So let me find what is it. So what is the Jacobian here? So the Jacobian here is, okay, maybe before that I need to write what are u and v, no? U and v we already wrote here. Now that let us convert in terms of x and y. So therefore, if you convert x equal to au and y equal to b, right? Now, so the Jacobian is given by derivative of x with respect to u, derivative of x with respect to v, okay, and derivative of y with respect to u, and derivative of y with respect to v. say I'm calculating ulta. It's not the Jacobian of uv with respect to xy. Jacobian of xy with respect to u. All right. So what is derivative of x with respect to u? That is a. Derivative of x with respect to v is 0. Derivative of y with respect to u is 0. With respect to v is. So what is the determinant? So the determinant is a into. All right. So now I got answer to the question. So now the A of R, that is area bounded by the ellipse, which equal to the Jacobian, that is AB into the area of transformed region. So that we already know, that is area of the circle. So that is A pi. So that is nothing but pi AB. So this is the area of the ellipse. In other words, this is what we wrote here. So area bounded by an ellipse is equal to Jacobian, okay, into area bounded by an circle. For a suitable transformation only, it is not the general formula, okay. For this kind of transformation only, it works. All right. Suppose if you use some other transformation, u equal to some x plus y and b equal to x minus y, then that ellipse may not become a circle. It may become some other shape. Okay, it may give you some parabola. It may give you some other shape. Okay, it may not remain as a circle. So for a suitable transformation only this one. Alright, so area bounded by the ellipse is simply AB, that is Jacobian, into pi, that is area of the unit circle. Okay, so if you see the use of Jacobian matrix, so the determinant of Jacobian matrix will tell us change in area whenever you apply some transformation. Okay, and this is going to be true whether for a linear transformation or for a non-linear transformation. See, for example, um, let us talk about a non-linear transformation, that is x equal to r cos theta and y equal to r sin. Okay, this is also a transformation. You are moving from xy coordinates to polar coordinates, that is r and theta. Okay, you're just changing the coordinates. Cartesian coordinates, polar coordinates. These are what we call Cartesian. These are polar coordinates. And this is what the relation between them. All right. Now, if I see the Jacobian, so the Jacobian, that is Jacobian of x comma y with respect to r comma theta, that will be equal to what is it? xr x theta, yr y theta, and which is nothing but, I hope we can write what is it? xr, derivative of x with respect to r is cos theta, and with respect to theta is minus r sine theta, and this is sine theta, and this is r cos theta. All right. So now its determinant is nothing but r cos square theta plus r sine square theta, and you can see this is r. So now, okay, what it tells us. So let's see geometrically what it tells us. So this is what the xy plane, x and y. All right. Similarly, you draw r and theta axis. This is r and theta, and just taking, okay. So here r may not take the negative values. Somehow you can define for r negative guys also by taking opposite. Let's say if I say -1 radius, and if the location is here, you may identify it here. I hope you have this minus r concept in PUC itself. don't know. Now I don't need that anyway. So here, so what it tells me is Jacobian is R, right? So the Jacobian we got R. Jacobian of xy with respect to R and theta. It means if I take a small change here, that is delta x into delta y, okay, and the area of this box is nothing but delta x into delta y. Now that box, it may be transformed like this here. This may be image of this guy. Okay. So now the question is, this is equal to, suppose if I express it in terms of delta r and delta theta. So how to express it? Now from the earlier calculation, we can actually write this is the Jacobian into delta r into delta theta. Okay, so it means what it is saying, if you are close to origin, the change in area is smaller, and if you are away from the origin, it means r will be bigger. It means the change in area is also bigger. It means if you take a small area which is very away from the origin, this far to the origin, then here this picture may transform like a bigger picture. So there is more expansion when you are far to the origin. And whereas if you are close to the origin, the expansion may be smaller. Okay. So that is why whenever in integral calculus for functions of several variables, we use Jacobian. I hope you must have studied this probability and statistics course. No, there you use double integrals. Okay, because in calculus and linear algebra, I hope you don't have this double integral topic, but in probability you may see it, right? Whenever you change the coordinates, I hope you might observe this dx into dy. You used to write Jacobian into uh, du dv. Maybe if you don't notice it, at least you would have noticed this. That is dx into dy equal to r into dr d theta. When you move to polar coordinates, so dx dy we will change it to r into dr d theta. Generally, the double integral, this is how we write. Double integral of f of x comma y over some region r into dA, where dA is nothing but dx into dy, the small portion of area in the xy plane. That we write it with dx into dy. Okay. So now if you change it to new coordinates, so in new coordinates we will write this. The transformed region after applying transformation into f of r comma theta into, so we write r dr d. Okay, so in place of x, of course, you are going to substitute r cos theta and r sin theta. Finally, it becomes function of r comma theta. That's what I wrote. It's not that replace x and y with r and theta. It's not that I'm saying. Let me write some capital F. Okay. So this is one of the use of Jacobian matrix, and not only this, in stability analysis also we can see the use of Jacobian matrix, and you can actually see this Jacobian matrix as a derivative of the transformation also. What I mean, for example, you have a, a function. I hope so far you must have studied only single variable functions. Now let us see what is not single variable, a real valued function you must have studied. Alright, scalar valued function. Now let us see what is a vector valued function. So far you might see a function from R3 to R4 Okay, and a function from R4 to R like that. But now let's think about a function from, let's say, R3 to R2. Yeah, you may say, sir, we studied linear transformations. Yeah, linear transformations we studied, but non-linear functions we didn't study, right? So now I'm taking a function f from, let's say, R2 to R2. Okay, and this is how it is defined: f of x comma y. Let me write it as capital F of x comma y, and this equal to f1 of x comma y comma f2 of x comma y. All right. Now this is a function from R2 to R2. So if you observe it, the component here, the component here, this is again a function of x comma y, and this f1 is actually a function from R2 to R. Okay, and f2 is again a function from R2 to R. Simply what we have done here is we have taken Cartesian product of these two functions. That is what our capital F. And the output, instead of getting a single value, we got it like a vector form, an array form. So that's why we call it as a vector value. Okay. So now if you talk about the derivative of a function, and the one which is going to help us is the Jacobian. Okay. So now you see what is the Jacobian of this one, Jacobian matrix. So the Jacobian of f1 comma f2 is nothing but first derivative of f1 with respect to x, and derivative of f2 with respect to y. Next, sorry, derivative of f1 only with respect to y. And similarly, derivative of f2 with respect to x, and derivative of f2 with respect to y. Okay. Similarly, if you have a function from R3 to R3, okay. So then what is f of xy? Now f of xyz, three variables will come. Alright. So now here I have f1 and f2 and f3. So each fi is a function of xyz again. Now if you see what is the Jacobian of f1, f2, f3, and you may simply write it like this also, df. Right. And this is nothing but the matrix which is given by derivative of f1 with respect to x, f1 with respect to y, and f1 with respect to z. Similarly, we write it for f2. Okay, so this is the Jacobian matrix for this function, right? And of course, you can write a Jacobian matrix for R3 to R2 also. So in that case, what happens? Let's say if you have a function from R3 to R2, okay, and how is it going to be defined? F of x, y, z, which is equal to just two functions, f1 and f2. But here, in this case, the Jacobian matrix is not going to be a square matrix. You will get a rectangular matrix because there are only two functions here, but three variables. And similarly, Jacobian of f with respect to f2 with respect to x, f2 with respect to y, and f2 with respect to z. Okay. So this is how you can simply find the Jacobian matrix. You can think of it as a derivative of a function also. Yeah, functionally dependent. So now let's assume that you are actually given with two functions like this. One is u of x comma y, which is x square plus y square, and v of x comma y. Okay. And this is actually, let me assume this is x plus y. I'm taking a trivial one only, x plus y whole square minus. If I take minus 2xy now, it becomes it is equal to just x square plus y square. So there's no point in taking it. Alright. So supposing you have two functions, okay, u of x comma y and v of x comma y, and if you find that this Jacobian I mean determinant. So if I say Jacobian matrix, we will write the matrix only. But the Jacobian, we will take the determinant of the Jacobian matrix. So the Jacobian of uv with respect to xy, if you find that it is equal to 0, suppose it is equal to 0, then definitely, then there exists a function f such that this f of u comma v will become 0. Okay, it means these two functions u and v, this u and v are functionally dependent. You know what is linearly dependent, right? If there exists a linear combination that is equal to 0 where the scalars, not all scalars are 0, then you say it is linearly dependent. Now we say these guys are functionally dependent if there exists a function so that f of these guys is equal to 0. Okay. So let me give you some example here. So if I take u equal to x square minus y square by x square plus y square. Okay, and v equal to, you take xy by x square plus y square. So these are the two guys I'm taking. Now you do one thing. All of you do it, okay? So you find what is the Jacobian. That is Jacobian of uv with respect to xy. Take it and do it. Alright. So if you do it, you're going to find it is 0. Okay, you know why? It is 0 because these two guys are functionally dependent. It is there exists some function so that f of u comma v will give you 0. Okay, let me tell you what is the function. Now that f of u comma v is nothing but how about u square plus v square minus 1? You directly square it. U square, if you take u square here, that is x square minus y square whole square. Y in the denominator I have x square plus y square, that is fine, and I need to take square of it, plus v square. Okay, just if I take xy whole square, that may not help me. Let me do one thing. Let me multiply with 4 also. So here it is 4v square minus 1. So this is 4 into x square y square divided by x square plus y square whole square minus 1. Now if you observe that, if you combine this expression, what is it you get? I hope you know this is a minus b whole square minus plus 4ab, and that equal to a plus b whole square. Okay, so using that, since the denominator is common, I can simply write x square plus y square whole square, the same denominator for both. And if you look at the numerator, it becomes x square plus y square whole square using this one. Okay, minus 1 you have, and this is same as 1 minus 1, and we got 0. So you try to see, we have a function here, a function of u comma v, so that f of u comma v is 0. So to know whether two functions are functionally dependent or not, like u of x comma y of x comma y is functionally dependent or not, you can simply use Jacob of these two. If they're functionally dependent, if it is not 0, then they are functionally independent. It means there is no function so that f of u comma v will become 0. That's what we mean by independent. And of course, whenever the determinant is non-zero, then in that case, there will be no dimensionality loss also. But if the determinant is 0, there will be a dimensionality loss. Means R2 to R2, and further transformation if the Jacobian is 0, then you may go from 2 dimension to 1 dimension or 0 dimension. You will lose the dimension there. It's like taking every point on R2, simply projecting onto the x-axis. So if you're projecting onto the x-axis, what happened? You killed that y-axis dimension. All right. Now the image is going to be just x-axis. So the dimension got killed, and you can observe that the Jacobian for that is 0. So even for the non-linear functions also you can observe. And this Jacobian matrix will help us in knowing whether the transformation is invertible or not. When it is non-zero, we can see that the transformation is invertible. All right. So this is all about Jacobian matrix. Yeah, here I'll stop it. I told you up to 8, but yeah. Anyway, we started late, so we end up with. Okay. So any questions or doubts? Okay, so if no questions, we will meet in the next class. So in the next class, I'll discuss the Hessian matrix and the convex function and convex sets. And later we can move to this optimization. All right. So I'll stop it here.